Hi everyone, welcome back. Today we're going to continue on and move into the new section of Algebra 2 Trig, and we're going to be focusing on vectors. So the title of today's section is 7.3, Vectors in the Plane. The essential question is, what is a vector and how do I represent them as directed line segments and write their component form? So in this part right here, I've kind of written down the key points, and I want to go ahead and walk through them as well as use the book for additional reference. So first off, why do we use vectors and what's the point of them? So in terms of math, when we calculate things, we're usually calculating things like temperature, value, very set things like money, area, time. So things that don't have additional features to them. However, once you get beyond those things, and we're talking about more in-depth, kind of three-dimensional in a way, and we're talking about stuff in physics like force and velocity, then that's when we have to talk about and show our answers in a different way. Vectors let us do that because vectors allow us to represent this idea of magnitude as well as direction. So when we're talking about magnitude, it's talking kind of like about the strength, the speed, how much of something is happening. Direction, a little more self-explanatory, is talking about which way we're going. So here, if you look at my vector v, I have a line segment drawn, and vectors are always drawn as directed line segments. Basically, it's just a line segment with an arrow on it, which shows which way it's going. The reason that's important is because if I had drawn the arrow going this way, for example, that would be showing a directed line segment or a vector that's going southwest versus my actual directed line segment here. This is a northeast direction. Okay? Magnitude, this is the notation for magnitude, and basically the way we find magnitude using vectors is just by using the distance formula. So finding the distance from this point to that point. And that will represent how far, how strong something is going. Okay? Now here I wrote three different letters, V, U, W. You really can use any letter to represent your vectors, but these are the more common ones. And they're always written in lowercase and in bold. Right? So for this entire setup that I have here, my vector V, as labeled right there, is equal to the directed line segment PQ. Now, some of you might be wondering, wait, what's the difference between a vector and a line segment? If you actually, I'm going to save that for the next example because it will be a little more apparent as to why we differentiate them. So first off, let's go ahead and do example 1. We're going to show that the directed line segment PQ and RS have the same magnitude. Thus, we're also going to prove that perhaps two vectors can be the same thing. So let's go ahead and work out this problem. Let me set this up. All right, so to do this problem, we're going to have a small coordinate plane with just quadrant 1 as our focus for now. We're going to have one directed line segment starting at 0, 0 with an initial point. And before I go on, actually, I wanted to mention, all directed line segments have an initial point, in other words, where they're starting, and a terminal point. We generally go with the letters PQ. When you write it as a directed line segment, P will be the first one, because that's where you're starting, and Q will be the second one, that's where you're ending. So really, it's whatever letter you're using. Here, notice that we start off with just a line, and then we end with this little hook, half arrow. Basically, you want to make sure you start with the initial and then end with the terminal in order to have the correct notation. Okay, just to make note of that. So here, 0, 0, I'm going to have a vector that ends at 3, 2. So 1, 2, 3, 1, 2. And I'm going to also label these points just so we don't get confused. See if I have a different color to switch to. Yeah. The next one will be at 1, 2. ending at 4, 4. 1, 2, 3, 4, 1, 2, 3, 4. All right, so we do have two directed line segments going the same direction, so that's kind of a hint as to what's going to happen soon. And they are notated by different letters, so this is going to be called vector v, and this is going to be called vector u. All right, so our goal is to find and determine if they have the same magnitude. So the magnitude of the first one, PQ, using the distance formula, will be, let's start off with x2 minus x1 squared plus y2 minus y1 squared. That's going to be the square root of 3 squared, so that's 9. 2 squared, that's 4. So we have the square root of 13. Let's go and find the magnitude of the other one then. So the magnitude of RS is equal to the square root. It's 4, 4. 1, 2, already there. So 4 minus 1 squared plus 4 minus 2 squared. 4 minus 1, that's 3. 3 squared, once again, is 9. 4 minus 2, that's 2. 2 squared is 4. And we find out they have the exact same magnitude. So I can confirm right now that yes, the magnitude of PQ is equal to the magnitude of RS. And that was our original question. Now, there is a further step that we can another bit of information we can extract from all this. We know that they have the same magnitude, and we also know they're going in the same direction because, well, obviously they're both going to the northeast. Because these two directed line segments have the same direction and the same magnitude, they're actually the same vector. Even though they're in different places, they are still the same vector. And we're going to kind of denote that by saying that vector u, and I should write this, so vector u equals vector v. And that's what I wanted to point out earlier, is that the book kind of mentions right here, two directed line segments that have the same magnitude and direction are equivalent. For example, all of these guys over here are equivalent to this one, the original directed line segment PQ. Because of that, even though they're drawn all over the place, they're not exactly in the same location, they still have the same direction and they have the same magnitude. So this entire set of line segments, directed line segments, are the vector v. So I can call all of these vector v, even though they do look a little bit different from our original vector v. So in this problem, example 1, calling them different vectors is actually a bit wrong here, because even though they're in different spots and we call them different vector names, they're still the same because they have the same direction and the same magnitude. All right, so that's the first idea of idea of vectors that we want to get across. And the second one is how we can write the notation for a vector in something called component form. Now, the whole point of component form, let's go and refer to the book real quickly, and you will have some things to copy down. So a vector whose initial point is at the origin 0, 0 can be represented by the coordinates of its terminal point, v1, v2. This is the component form of a vector v. Now, what's the reason of doing this? It's something like this. Over here. If I had found the component form for my vector v, I'm going to show the math in just a little bit, but it would end up having the exact same component form as this. And the reason it would have the same is because it's the exact same vector. So again, I will show it in just a moment, but the difference between the vector that was on top is that it wasn't at the origin, versus the other one did start at the origin. So component form, sorry for switching back and forth so much, is that we're referring to a vector whose initial point is at the origin. And we want to describe vector in that way, rather than talking about where it's coming from, like out of nowhere. It might be in the middle of the fourth quadrant, or going through the third quadrant, but we want to focus on where did it begin, or where would it have begun if it started at the origin. So what I want you guys to copy down right now is the component form of the vector, and go and write down this entire equation. If you need to, write down the magnitude as well. It's pretty much just a distance formula, but if you need to, feel free. I'm going to go ahead and move on to example 2 now. And example 2, it's going to be a lot of writing, but not that difficult. Example 2 is going to ask you to find the component form of the vector v. I got to make sure I bold this for correct notation. And the vector v with initial points 4, -7, and terminal point -1, 5. So if you had chosen to graph out this vector, what you would get is this right here. And as nice as that is, we want to know what would be the coordinates of this vector, the terminating point of this vector, if it had started at the origin instead. So we're going to go ahead and use that component form formula that you guys just copied down. And let's go ahead and figure out where would it have ended if it started at the origin. So first off, let's go ahead and label these. P will be our initial point, so let's call P 4, -7. And then Q will be -1, 5. Now because they did say P1, P2, all that stuff, let's go ahead and label P1, P2, Q1, Q2. And now we're going to find the component form of this vector using this. So PQ, make sure to have this notation. This is to show the component form. Q1 is -1, -4, comma, Q2, 5, minus P2. So the component form will be received or found after we simplify this. So here we go, -5 and +12. And that is going to be the component form for my vector v. So again, if I had started at the origin and drawn my vector starting from the origin, this would be where its terminal point would be. So rather than looking like this, this vector, coming from here, going all the way here, it would instead start at 0 and go all the way to -5, 12, so somewhere over there instead. Okay? And that's the idea of the component form. We're not going to graph it for today, but you might have to in tomorrow's lesson, so just make sure you understand that point. Alright, hopefully everything made sense. This is pretty much an intro to vectors. We will be doing a lot more with them the rest of the week. Write down any questions that you have, and we'll see you tomorrow.